Okay, so our first talk this afternoon is by Dr. Julie Simon and her team, and they'll do an update on the Biomedical Acoustics group.
Excellent, thank you. Welcome everybody. I think we're the newest group for the CAVs. So the biomedical, can you hear me now? Perfect. So we're the Biomedical Acoustics group. I think we're the newest group. We had 10 faculty until just recently, and then we had 2 new faculty that joined. So we have Amanda Chase from the Applied Research Laboratory just joined our group, and then also Mehdi Kiani from Electrical Engineering and Computer Science has also just joined our group. So very excited to have them, and we'll learn more about Mehdi Kiani's research, both his students presenting today in addition to one of my students, and then he's also agreed to give a CAV seminar that I believe we've tentatively planned for November 16th. So we do have a seminar scheduled from a PSU student, or PSU group. Group activities, we did have a great speaker for spring. A good friend of mine, Hong Chen, agreed to give the Zoom seminar on targeting the brain with ultrasound. So if you're interested in any brain therapies, they're moving more and more into the clinic, and so if you're very interested, she gave a great talk, and I believe it's on the CAV website. And then we do have one planned for this fall right before Thanksgiving, I believe. So stay tuned for those updates. Whereas there's one student poster we're going to claim. They already gave their overview, so I won't dwell too much on that. And then we did have one student graduate out of Scott Medina's lab in biomedical engineering. Jano designed some really cool perfluorocarbon droplets that when you hit them with acoustics, they change phase to gas bubbles that we can then detect or pop and cause drug delivery. So some really cool work. Her thesis should be on the CAV website, I think, in the near future. And so I'm going to go ahead and turn the stage over first to Eric Rockney. He's out of my lab group, who will talk on the color Doppler ultrasound twinkling artifact on pathological mineralizations. Then we'll have Sheikh Ilham, who's a Mehdi Kiani student, about ultrasound phased arrays for large-scale ultrasound neuromodulation.
Thank you. So as she said, my name is Eric Rockney. I'm a 4th-year PhD student working in her lab. And today I'm going to be talking about the color Doppler ultrasound twinkling artifact, specifically in pathological mineralizations. So to begin, I'll talk a little bit about what a pathological mineralization is. A pathological mineralization is a crystallization that can form in the body due to a disease. The most common one that you might think of is kidney stones. Kidney stones form from a variety of chemicals in a complex matrix of proteins. It can cause a lot of problems, pain, so being able to detect and treat these is very important. Some other ones that can occur: gout forms as uric acid crystals in joints. This can cause pain, inflammation, arthritis. Some atherosclerotic plaques can form cholesterol crystals. These crystals typically indicate a more mature plaque and can sometimes indicate the likeliness of the plaque rupturing. So being able to detect these is very important, especially early on. Heterotopic ossification, or bone growth in soft tissue, can occur after some traumatic brain injuries. These form as calcium phosphate crystals. And then some breast cancer tumors can form microcalcifications as either calcium phosphate or calcium oxalate crystals. And these can sometimes indicate the malignancy of these tumors. So potentially being able to determine what type of crystal is there can be important for treatment. Now, a common theme among all of these pathological mineralizations is that they can be difficult to detect and diagnose early on. Some methods for detection include taking a blood or fluid sample from the infected area. This, of course, is slightly invasive and is a somewhat difficult procedure to do, especially before you know that the crystal is there. And so early detection is difficult with this. CT and PET scans are considered the gold standard for detecting these mineralizations. However, it uses ionizing radiation, which is something that we want to avoid with our detection methods. And it's also a fairly expensive procedure. And this brings us to the acoustics, which is ultrasound. Now, this is B-mode ultrasound. It's a non-invasive, fairly inexpensive and easy method that can be used to detect pathological mineralizations. However, oftentimes, this B-mode ultrasound is not sensitive enough to actually be able to distinguish the mineralization from the surrounding tissue. And so other modalities of ultrasound can sometimes be used to help increase that sensitivity. And that brings us to the color Doppler ultrasound. So Doppler ultrasound is another modality of ultrasound that is typically used to look at blood flow. It operates on the Doppler principle, where flow moving to or away from the transducer gives you either a blue or a red color shift in the image to indicate what flow is occurring in the body. Now, Doppler ultrasound back in the 90s was actually used by a man named Ramuni to image kidney stones in vivo. And what he found was that this rapid color shift appeared on these kidney stones, suggesting that these stones were rapidly shifting and rapidly moving. But of course, they're just sitting in there. And so a question arose as to what is actually causing this rapid color shift. Two main hypotheses emerged. The first is that there was some machine or signal processing that was causing this artifact in the signal. And the other is that there's an actual acoustical physical phenomenon that's occurring. Now, in the vein of this second hypothesis, researchers at Washington University back in 2013 imaged kidney stones in ambient conditions and again in overpressure situation. And what they found was that twinkling actually decreased in the overpressure situation. And then when it was brought back to ambient conditions, the twinkling reappeared. And their theory for what was happening here was that there is a bubble that forms, or there are microbubbles that are formed and stabilized in crevices on or within the kidney stones. And when the ultrasound interacts with the bubble oscillates slightly, and then the resulting backscatter from that bubble causes this perceived random motion in the Doppler signal. Now, the twinkling artifact has been studied extensively in kidney stones. Not as much work has been done in other pathological mineralizations, but it has been seen in some other of these mineralizations. And so the question has become, does the twinkling artifact appear on crystalline structures in general? And so that's what the first part of my research is looking at. To do this, I've grown 3 different types of crystals that are commonly found in pathological mineralizations: uric acid, cholesterol, and calcium phosphate. I grew these from a supersaturated solution of these various chemicals and adjusted the pH and temperature to specific values. Then to evaluate the twinkling artifact on these crystals, I used a setup that we can see here, where we have a crystal sitting in a water bath, deionized and degassed, and then an L74 transducer, which is a linear array with 128 elements, operating at 5 megahertz, scanning from above. Here are the typical imaging parameters that we would use and an example waveform where we have pressure versus time. And with this L74 transducer, it was connected to a Verisonics research ultrasound system, which allowed us to actually save the IQ data resulting from the Doppler signals. So what I would do is actually mechanically scan this transducer across the crystal using a step size of about 0.01 centimeters. And at each scanning location, I would save 2 frames of the IQ data and average them together. And then using all of these scanning steps, I was able to compile 3D maps of the Doppler signal to look at the twinkling over the entire crystal and also quantify how much twinkling we saw. The way I quantified it was I took a region of interest around the crystal. Here we have the Doppler magnitude, and divided out a background box that was size and depth matched, summed it across the entire crystal scan, and then using this equation, calculated a pseudo dB Doppler power value that was able to be compared between the crystal types. And an ANOVA was used to calculate the significance between the different crystal types with a significance value of 0.05. And so here are the results. These are representative 3D maps of the Doppler magnitude, where orange and above represents twinkling here. And what we can see is that on all three crystal types, twinkling actually appeared, suggesting that these crystal types in particular are able to produce the twinkling artifact. Looking at how much these twinkled, we have the Doppler power on the y-axis, which is telling us the amount of twinkling. And we can see that in cholesterol, it twinkled significantly more than in uric acid and calcium phosphate. I'll come back to that in a little bit. But now that we see that these crystals are able to twinkle, the question becomes, are bubbles also causing the twinkling in these crystals like they were in kidney stones? And so that leads me to the next part of my work, which is essentially recreating the experiment that was done at University of Washington. So here I have a pressure chamber that was made in-house, where we would scan the crystal with, again, the L74 transducer. And over time, I would increase the pressure using this hydraulic hand pump and record the IQ data and observe how twinkling changes as pressure changes. And what we found here, I'll walk you through this graph right here. So we have on the left side and in the blue, the normalized Doppler magnitude, so how much these crystals are twinkling over time. And then on the right side, we have how the pressure is being changed around the crystal. And what we can see is that as pressure is being increased, the amount of twinkling seen on each crystal decreases. And then when it's brought back to the ambient conditions, the twinkling again increased. And this was consistent between all three different crystal types that I tested. Uric acid, some of them weren't as consistent, and so more studies are needed for those. But overall, our conclusions that we were able to come to from this is that pure crystals, at least in these three cases, can produce the twinkling artifact. And what we found was that cholesterol crystals twinkled the most compared to the other two. This could have something to do with the fact that cholesterol is hydrophobic, which could lead to more bubbles potentially forming and creating more of the twinkling artifact. And then from that last experiment, we were able to say that bubbles are likely causing the twinkling on these crystals like we saw in kidney stones. So moving forward, some future work that I want to accomplish is actually visualizing these microbubbles in these crystals, something that I've done in kidney stones using microcomputed tomography. Also looking to see how additional factors such as surface tension and the gas content affect the twinkling artifact. And then also I want to actually model crevice bubbles in an ultrasound field experimentally and computationally and compare those results. So quickly want to acknowledge the funding that we have for this, the NSF Career and GRFP, and then the rest of our lab that's supported me, the Basel lab. Thank you. I don't know if questions will be now or later, but I think we could maybe just move on.
No, I think
Questions?
Yeah, people tend to forget when you move on to the next speaker. So yeah, we'll take a couple of questions now, and then we can move on. Anybody ever had a kidney stone? So the methodology you mentioned that you used to visualize on kidney stone, I remember you presenting it before. Maybe you can give a quick overview of what you plan to do with that for the crystals here?
With the microcomputed tomography? Mm-hmm. Yeah, so with the kidney stones, what we did was we imaged the kidney stones with microcomputed tomography. Here at Penn State, we have actually a really powerful one that allows us to image it underwater. And so we would image the kidney stones degassed underwater and then pull vacuum on it. And while it's still in the same position, image it again. And then compare between the two. And theoretically, if there are bubbles in there, in the vacuum, when vacuum is pulled, the bubbles will expand. And so that's how we'd be able to visualize whether there's some sort of gas inside of the kidney stones. And looking to do pretty much the same thing with the crystals, just to confirm or deny that there are bubbles in there.
All right, neat. Okay, thanks again. Let's give a quick hand. Okay, and next up.
Hi, good afternoon, everyone. I'm Sheikh Ilham, and my PI is Dr. Mehdi Kiani. Thanks to CAV for giving me the opportunity to present my work here. So the work is on ultrasound phased array optimization for large-scale ultrasound neuromodulation. Oh, sorry. Okay. So the background briefly, conventional transcranial ultrasound neuromodulation often involves single element transducers, which often use bulky apertures, which is not suitable for neuromodulation in live animals. So to come up with some solution, this is a good strategy, like using ultrasound phased array, as those can be electronically steer or focus the beam and target different locations. And also we can create our own miniaturized electronics or ASICs to drive those. But for the design, we need to consider a few things. For neuromodulation, it's very important to have enough pressure and also small focal volume. And also, we want to minimize the electrical input power. As well, we want to attenuate undesired stimulation. So we can achieve these things if we consider the design parameters and we design in a systematic way. So say, for example, for a linear phased arrays, these are some important parameters, like inter-element spacing, which is denoted as D, the element width, which is A, and also like the aperture, which is capital D here. So these are some important parameters to consider. So actually, in my work, I propose a method to systematically optimize these parameters. And say for example, for neuromodulation of a rat model, the total aperture cannot be more than 25 millimeter because we have to set it on the, say, on the head of a rat. And also, like, we want to target a focal, say, the depth of the brain is like 12 millimeters. So these are some constraints. So actually, this is the flowchart that we will follow to optimize our phased array. So we will first start from considering the constraints that are coming from the application or also from the fabrication. And then we'll start to optimize the element length, element width, inter-element spacing in an iterative way. We will maximize a figure of merit, which I can explain it in the next slide. And then we will optimize for some directivity plot, which is related to minimize off-target stimulation, which is important for neuromodulation. And then actually we will optimize the thickness. We will do it in COMSOL simulations. So some more details on the optimization procedure. As I said, we use K-wave simulations for the optimization. So say this is a structure in K-wave. So we have like our scanning plane in XY and XZ planes. So we do the acoustic fields recording like this in XY plane, XZ plane, and we calculate the area and the width in the elevation direction. Then we calculate the volume, and overall we calculate the figure of merit that we defined to maximize the pressure. As you can see from the definition of the FOM, if you follow, the pressure has to be maximum, the volume has to be minimum, and also like a term square root of NL that is required for considering the input electrical power. That is another optimization. So then we use the COMSOL simulations like this, single element, and we optimize our thickness so that we meet the target resonant frequency. And that's how we get our optimum parameters. And then the results. So for one particular example, say we optimize the element length and get the maximum FOM. Then we optimize element width and inter-element spacing for a maximum FOM. Similarly, this is a directivity plot. I mean, this is not directly directivity plot, but something equivalent. So from here, we can actually identify what is the maximum inter-element spacing we can use. And then this is the result for COMSOL simulation to optimize the frequency. Then we also optimize the number of elements, because this is important for designing electronics. Because expense of the electronic design will depend on how many number of channels you want to design. And also, this is an example of just beam steering simulation just to check for steering capabilities. And then the next step is fabrication. Once we do the optimization, then we start from the very scratch, the design, like we design the PCBs according to the optimized parameters, and we use bulk PCB, and we dice it, we solder it, wire bond it, and encapsulate it. The whole device is now ready to go. Sorry. And then we characterize electrical impedance for each of the elements, and also like the pressure generated by each of the elements. So then time for the measurement. So this is the measurement setup. That is an automated setup. It can scan 2D or 3D fields, whatever you want. And it's totally automated. And so there are some results, more results. Basically, the measurement results. So as you can see, these are the 2D beam profiles. So first, 1-1 comparison of simulation versus measurement, which are pretty close in XY plane and XZ plane. This was for this particular example, say the nominal focal distance was 12 millimeter. In that distance, we got this. And then we have more results, like we checked for beam steering capability and the beam profiles in 45, minus 45 degree. Then we have more results, like so nominal distance was 12 millimeter. We have beams in 8 millimeter. I mean, a little less distance from the nominal, and bigger distance, like 16 millimeter. We get these profiles, and which are theoretically, I mean, in agreement with the simulations. Sorry. And also, finally, what we did, like, we wanted to see the effect of, say, because the target was neuromodulation, so there will be lots of aberrations coming from the skull, those kinds of things. So we had the last measurement, say, with the presence of hydrated rat skull to see how the beams are affected. And finally, the future application. Basically, once we started this project, the first thing was the proof of concept of like the animal studies. But that time we did it with single element transducer. So if you just see the video first. So if you follow, the red light is blinking, means I'm giving the ultrasound stimulation in a burst mode. And then if you follow, you can see the movement of the tail. There is a latency, but it's the effect of that ultrasound stimulation directly on the brain. So at that time, we actually characterize the beam profiles and the pressure that we need. We found that around 1 megapascal pressure enabled us to get this result. So then we started to design that array, which will give us that electronically beam steering and focusing capability. But at the same time, we want to generate the same sort of pressure, like around 1 megapascal. So that was the, motivation behind this. And yeah, that's pretty much it. And if you have any question, please go ahead.
Okay, questions?
How large are your driving electronics for your array? You mentioned you wanted to be able to do it on live animals. And so have you been able to minimize your driving electronics, or are they still attached to some sort of RF amplifier?
Thank you for your question. So basically, for the amplifier, we can design a small chip, which, and also the, say, the driver electronics is a board of, say, 40 millimeter by 40 millimeter. And actually, we are also parallelly developing that board, which we, in near future, we will implement that board to drive these electronics. Currently, still, we are using some commercial driver board, but that is still small, like 15 to 20 millimeter by 20 millimeter. Yeah.
So 1 megapascal, that sounds like rather a lot to me.
Yeah, 1 megapascal.
Yeah, is that doing any permanent deformation or damage inside the animal itself?
Yeah,
that's a very high stress.
That's a good question. So that's something actually we need to do histology or that kind of thing to understand. But from the previous studies, it seems this is like some sort of pressure that they use or generate for the neuromodulation, because there is a skull and there will be some sort of attenuation, and after that will reach there. So it should be good at this point, yeah.
Okay, any other questions? Yeah, Andy in the back there.
Thank you. On your simulation versus measurement slide, it looked like at least for the 0 degree impact, the measurement was off a little bit. Was that just due to misalignment, or is that something with the transducer itself?
Thank you for your question. Yes, that's because for our current setup, there is no rotational angular setup that can exactly measure the angle. So there might be a misalignment of the transducer and the hydrophone, which resulted in that.
Got it. Thanks.
Thank you.
Okay, yeah, neat stuff. Thanks again.
Thank you.